This video is for chapter 11.3. This is part one. We're going to look at making inferences or doing hypothesis tests for two samples, uh, that are independent. And so you have your note sheets out. You can see we have the series of steps needed to conduct a hypothesis test. It's going to follow the same format as we've been doing. Again, you might encounter in your homework, the online homework, this statement of Welch's T. We use this in this example, but again, since we're using StatCrunch, we're not going to do the hand calculation. Just be aware that when we're doing our two sample independent mean tests, the standard deviations are unknown in most of the cases, and so we use this situation of Welch's T. We use a Welch's T distribution, but again, since we are, and this is the formula there, but since we are using StatCrunch, we don't have to worry about that. Just be aware you might hear that term. Of course, to run these tests, we have to make sure these conditions are met. You've seen these before. And then we run a hypothesis test. Notice the notation, the mu of 1, mu of 2. Now we're comparing two different samples against each other versus the difference between the samples. We're actually going to get the mean of 1, the mean of 2, and then compare them together. So the notation is different than we had before. And then all the steps are the same. Alpha level, which is our type 1 error. Get a test statistic, and we don't use the classic approach. We use the p-value approach. So let's go ahead and do our first example here. Here are the steps. You can read through them, but they're what we've had before. Here's the first situation. We have a space lab, life science. Payload 14 male rats were sent to space. Upon the return, the red blood cell mass of the rats were determined. A control group of 14 male rats was held under the same conditions as the space rats and their red blood cells determined. And so they're trying to see if there's a difference between those who were in the flight and those who stayed home, but under the same conditions, see if being in space affects them. Here's the data for them. And so we're going to run the hypothesis test on them. And so to run the hypothesis test, what we have in this case, we have, of course, you have the sample mean for the first group. We need, what is that equal to? We need the sample standard deviation for the first group. We need the mean for the second group, and then the standard deviation for the second group. We need those values. What we're interested in testing, does the evidence suggest that the flight animals have a different red blood cell mass? Different. And so in this case, what we're saying is that the flight rats, right, are somehow different than the control rats, those who stayed back at home under the same conditions. And so what needs to happen is we need to have a hypothesis and a null hypothesis and an alternative. I mean, the null is that the mean of 1 is equal to the mean of 2, which is always the case. And the alternative is that the mean of 1 is not equal to the mean of 2, that they're different. We wanted to run this test at alpha 0.05. This would be a two-tailed test, which is, again, would be important if we were using the classical approach, but we still want to understand that. And then we calculate the test statistic. So we're going to use a StatCrunch to do that. I entered the data because we do need the data to run a t-stat. Two sample, not paired this time. And this time I have the data. So we go with data. We have the flight and the control. And then we're going to run a hypothesis test. And so when we run this test here, make sure do not click this. We don't rule pool variances. We do not click that option. And then you can read in the book, there's a description of that. But again, that's a more specific case. So we don't do that one. And then we compute. Let's make sure we have this. We thought that one of them was going to be, different. So we give a not equals, and then you compute. And when you compute, again, you get a test statistic and a p-value. So I'm going to use negative 1.44 as our test statistic. Negative 1.44. your t is equal to negative 1.44. The p was 0.1627. And now we can make a decision here. We do not reject the null hypothesis since 0.1627 is bigger than alpha. What's our conclusion? There is not sufficient evidence to support the claim that that they have different, that they are the rats, that they have different mass, or what was it, red blood cell mass. Yep. So that they have different red blood cell mass. We do not have sufficient evidence to conclude that, because what happened is we did not reject this and we rejected that. And so if we run a confidence interval and look at the difference, what we should see is that the difference between them should not contain 0, because if they were, or sorry, it should contain 0, so because they're equal to each other. When we the difference, they're not equal to each other. Since we're concluding that they could be equal to 0, the confidence interval contains 0. So we just go ahead and do the same thing, but instead of a hypothesis test, just do a confidence interval, compute, and then you can see zeros between. You have negative 1.34, 134, and 237. 134 and 237. 134 and 237. This is a 95%. And so what does this mean? Do not reject. Do not reject a H0, since the confidence interval contains 0. 0 is actual possible value. That's why we don't reject it. And so with that confidence interval, we have the point estimate. You do the calculation. You should know how to do that by now. Add them, divided by 2. And then we're estimating the difference between their blood cells. We're 95% confident. It's between negative 1.34 and 2.37, which means that either one could be greater than the other, and that's why we do not reject. Here are the instructions to run your hypothesis tests in these situations. And then an additional way to kind of check this would be to make scatter plots of the data. And so if we had that data there where we have it, and look at, not scatter plots, I apologize. We wanted to make box plots of both of these datas. We could then compare them next to each other. We would be able to look at how they appear to next to each other side by side. So looking at them, you can see that because there's overlap here, because there's overlap in that we don't have, because there's overlap here, I would say that we do not have a difference between them. That's kind of how we would also use a box plot. So some of your homework assignments, there's going to be, they show you box plots to kind of compare the two. So now that we're comparing them, see how big, that's way too big, sorry. The fact that we're comparing those two, you can see that there is overlap between them. And so because there's overlap, because we actually have overlap, I'm trying to get it in here, because we actually have some overlap in the box plots, there we go. Now we can say, you know what, there's really no difference. Even though the flight's a little bit different, overall they're not, and that's why we would reject, or do not reject, the null hypothesis, because there actually is some overlap between them, right? We can't say there's a big difference. Now, if they had no overlap, then we're more likely to say reject the null hypothesis, right? that they're not equal to each other there. So that's what we're looking at.